For Zoom, okay. This is what we had seen in our previous class. If there was anything to take away from the previous class, it was this. What are the control signals to control different components in your data path? For a given instruction, not all controls will be asserted or deasserted. So we'll have to carefully decide which one is going to be asserted and which one is going to be deasserted. We started off with our ALU control first. The ALU is a very special unit which has its own mini control unit. The reason why ALU has its own control unit is to simplify the hardware, to reduce the bulk of your main control unit. What the main control unit is going to do, it's going to generate a 2-bit signal called ALU up. And this ALU control takes in that 2-bit signal ALU up, and it also takes the instruction pipe down to 0, which is a pumped field, in order to analyze what kind of power operation it is. Here's how this ALU control is going to work. If ALU up 1 and ALU up 2, if they are 0, 0, then that means it's a load store instruction, meaning that the ALU will be adding the immediate value with whatever RS value is. That's what it is going to do. Your add-I instruction is actually very similar to the load and store instruction. Both of them involve immediates, and both of them always perform addition. And therefore, even the add instruction is going to use the same code for ALU up. It's 0, 0. However, if ALU up is 1, 0, then that means it's going to be an R-type instruction, in which case the ALU control is going to see what is the value of the funct field. It's going to see what is the function code. If it is function code something like 100000, then that means it's an add instruction. If it is 00000, if I'm not wrong, it's a shift left logical instruction. Similarly, if it is 0, 1, then it is branch if equal. If it is 1, 1, then that means it's branch if not equal. Now, we have also seen some control signals that are used to control the data path. So please take 2 minutes of your time, 2 to 3 minutes of your time to quickly read this slide. Now, please remember that we are dealing with hardware, and this is something that you may have not done before in your previous computer science courses, where you may have just done a lot of programming. With hardware, it is oftentimes useful to revisit this information over and over again. So please go over this information for me for the next 3 minutes. Read what happens when these signals are asserted and deasserted. Mm-hmm. Mm-hmm. Okay. Memory is not read, right? Memory is not read. But why is the register destination here? Are we not writing it back to the register? It is an add-I instruction. So add-I, what it does is adds the immediate value to the RS register and stores it in the RT location. So register will be written. So it cannot be don't care. Yep. So go to home, go to processor figures. Go to processor, that's a 7. Yeah. So this is the figure that we have seen. We're talking about figures. Yeah. So yeah. So when you do an add instruction, the value of RS is added to the immediate value, and that should be stored in the RT register. It is stored in RT register, reg write is equal to 1. So it matters where what reg write should be. Right. So it should be 0, so that RT can be written. Right? It cannot be don't care. It will be don't care only for store word instruction. Those instructions where you are not changing the register file, where your output is not written into register file. All right. So are we good with these control signals? Okay. Now, what I would like for you to do is discuss with your partners, work in groups, and please trace the path for the branch if equal instruction and give me the values for reg dest, ALU source, mem to write, mem to reg, reg write, mem read, mem write, branch, ALU op signals. So we have 1, 2, 3, 4, 5, 6, 7, 8 signals. So I'll ask 8 groups randomly to help me out with this. So please make some noise and work with your peers.
I think it's for the
%% of grade.
Worry about worksheets?
Yeah.
Don't be. I don't go very hard on worksheets. So don't worry.
That's gonna be one.
Yeah, but the goal of the worksheet is to realize the mistakes, and this is learning. This is what I want.
Then you're gonna use memory, bring memory. RSA for the addresses, right?
That's correct. Your label is kind of like your immediate, right? It is that 15. So here's how it is when you compare RSA and so and then that sign extended is shifted by 2, added 2 plus 4, and that goes into that box so that branching. So what would be useful is just trace the pattern, which the VEQ instruction is going to do. And yes, we are not activating the right.
Oh, branch. Branch is one. Plus one. Daily will be 1 and 2 are 1, right?
Yeah. Yes.
The control that you're doing one. 1 is 0 for it. 0 for 1. 0, right? That's what 1 is.
That's hard to concentrate.
Hard why?
Not just me.
It's okay. So that's why you have to talk to your peers, right? All right. Okay. So jazz hands again, jazz hands. Now, what we are going to do is we are going to first trace the path. I'm going to trace the path for you on these slides. The path that I trace, components will be present in that path. You have to turn those components on and off, right? That's what needs to be done. That's how you're going to analyze any new instruction. You're going to see how the data path is going to work for a given instruction. For a given path, see what components are in that path. What you would need to do is turn them on or off. So let's trace it. So this is how the branching instruction actually works. So as I was discussing with Sam, your BEQ instruction, the first operand is going to be the RS register, then the RT register, followed by the label, which technically is actually your 15 or rather 16-bit immediate. Let's call it label. It's label immediate. Branching instruction is going to happen if RS is equal to RT. Since this is a branching instruction, the value of the branch flag is going to be 1. But this comparison, so this has to be done by what? Which one of these components is going to perform this comparison? The ALU, very good. So ALU is going to perform this comparison, which means we need to read the value of RS register. We need to read the value of the RT register. So let's trace that path. We need to get the value of the RS register for sure, which will come out of the read data 1, and RT has to go to read register 2, which it does. Out comes read data 2, which should go into the ALU. And in this way, I would have read RS and RT and I would have shoved it into the ALU unit for a comparison. The immediate, the label, what happens to it in a branching instruction is that label is first sign extended, and then it is shifted left by 2, and then it is added to PC plus 4. That's what happens to the label. And this is your label. The immediate field is your label. It goes up, 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 up. It is shifted left by 2. This is 4. This is the value of the program counter. So this is PC plus 4. They are added together, and it is presented right here. And it is presented right there. Now, depending on whether RS and RT are equal or not, your PC source is either going to be 0 or 1. Specifically, if RS and RT, if they are equal to each other, which means that branching should happen. So in that case, PC source is going to be equal to 1 to allow PC plus 4 plus sign extended label to pass through. If branching should not happen, PC source is going to be 0, in which case PC plus 4 will be coming out of that multiplexer, right? But nonetheless, this is the path. This is your data path for a branch of equal instruction. Now, carefully notice all the different components that are coming in between. Let's first talk about this register file. In branching instruction, I'm just reading the registers for comparison. Am I writing it? Am I writing something in the register? No. So what should be the value of reg write? 0. If I'm not writing at the registers, does it matter who is at the right port?
No.
It doesn't matter. So what should be the value of reg test?
0.
I don't care. We don't care, right? Remember the X symbol from digital logic, don't care? We don't care. If register write port is like shut off, it doesn't matter who is at the door, right? For example, if I'm not holding office hours, I don't care who is at the door, right? So it doesn't matter. Therefore, reg test is don't care. Reg test is don't care. Reg write is 0. Very good. Now, let's talk about this multiplexer. It's the read data 2, which is RT register that needs to pass through and go to the ALU. So let's say Marcos and T, what should be the value of ALU source? 0. Very good. When ALU source is 0, read data 2 is passed through. And that's pretty much it. That's pretty much it that you will have to do for this particular slide. So in this case, my answer would be, oh, I don't want to highlight. I want to write. So this is going to be don't care. ALU source is going to be 0. And yeah, what about mem to reg? X, very good. Because if I don't care who is at the right register port, similarly, I don't care what data is present at the right data, because writing is disabled anyway. The office hours are closed, so it doesn't matter who is there at the door, right? And therefore, mem to reg is going to be don't care. Reg write has to be 0, because when this is 0, because of that, I can put X's there. And mem read, am I reading the memory? No, I'm not reading the memory. Mem write, am I writing to the memory? No. Is it a branching instruction? Yeah. And for branch if equal, what's the code? Was it 0, 1? Okay, 0, 1. And there you go. There you go. That's the answer. Please discuss with your peers about these answers. And here's what I would also like for you to discuss. What is the benefit of placing X's instead of just hard zeros? Cheaper how? You're right, it's cheaper.
Cover more cases.
You can cover more cases. So those of you that have taken digital logic design,
It can be either 0 or 1.
yes, it can be either 0 or 1. So when you place those X's in the Carnot maps, you can use those X's to group along with 1s and simplify your logic. The simpler the hardware, the faster it can run. It doesn't matter for this class, but it's a good general knowledge nonetheless. So those are control signals. So those are the control signals that we are setting to enable this data. Okay. So have a chat with each other. Have a chat for the next 2 minutes about this. Branch one is So we are going to talk about PC source first.
And then there's another right? Yes.
No, branch and PC source are not the same. PC source is a function of branch.
Yeah.
Yeah.
You don't read any data, exactly. No reading
I'll
data.
show you.
The read data, there's no, you're not gonna read the alien by zero. They're both actually used. I can get that. They're both.
What about the development?
Part of it does matter. I'll tell you. Yeah.
Like,
But those are very good questions. I am liking how you're thinking ahead.
What is it? Alias, right, yes, right?
Okay. All right. Now notice that bolded signal. Notice that bolded signal PC source, because technically it is the PC source that is going to decide between sign extended, shifted left by 2, plus PC plus 4, branch target, or just normal PC plus 4. So that PC source is going to determine whether I should go to the branch target address or whether I should just increment normally and go to the next instruction. Now let's talk about PC source. And this is just for general knowledge for you. Just to recap how digital logic ties into computer organization and computer architecture. We are going to see how PC source is actually generated. Your main control unit does everything. So that's why this is a big bubble right here, the main control unit. Your main control unit takes in just those 6 bits, 31 down to 26, which is the opcode, which tells the main control what kind of operation it is. Within this main control, there is a branching control, which is going to generate the PC source, which will determine whether to branch or not. Now, these are the inputs for this branch control. There is going to be a branch flag, right? If it is a BEQ instruction or a BNE instruction, branch flag is equal to 1. If it is not a branching instruction, like load word, store word, add I, branch will be 0. Additionally, main control sends to the branch control 2 more signals, ALU op1 and ALU op2. When ALU op1 and ALU op2 are 0 and 1, then that means it's a BEQ instruction. However, if it is 1, 1, then that means it's a BNE instruction. That matters because both of these instructions use 0 flag in a different way. In both of these instructions, branch if equal and branch if not equal, we are comparing 2 registers. And this is how the ALU compares. It subtracts those 2 values. That's how it does. It subtracts those 2 values. If the result is 0, then that means they are equal. If the result is not 0, then that means they are unequal. For example, if the register values are 5 and 5, 5 minus 5 is what? 0. So 0 flag will be set. If one is 5 and the other one is 6, what is 5 minus 6? -1, not a 0. Therefore, the 0 flag will not be set. So the branch control unit, it takes the ALU op1, ALU op2 to differentiate between BEQ and BNE. It takes in the branch flag to determine whether if it is indeed BEQ or BNE, and the 0 flag from the ALU unit to generate the PC source. What I would like for you to do next is discuss with your partners, work in groups, and give me a nice truth table. Many of us have seen truth table, right? In digital logic. How about in computing theory? Not computing theory, discrete math. Yeah. So you guys are like experts in truth table. So, okay. These are the inputs, ALU op1, ALU op2, then you have the branch instruction, right? These are the 3 inputs to the branch control. And since these are 3 values, so there are 8 possible combinations. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. For these values of ALU op branch, for these values of ALU op1, ALU op2, and branch, determine what should be the value of PC source. Now remember, for BEQ, ALU of 1 and ALU of 2 is 0, 1. For BNE, it is 1, 1. So please work with your partners and fill out this truth table.
Yeah, it doesn't matter. They're zero and those zero difference. Now it's zero No, the 0, 1 is going to be these. 0, 1, 0. Oh, yeah, so ilio is 1. Ilio off is 2. Sorry, ilio off is 1. 0, 1. That's going to be so it's 0. Okay.
Oh yeah, there's a 0 flag missing. Oh, my apologies.
Yes, I'm thinking something.
Something is missing, right? Thank you, thank you. That's why I would like for you to keep talking, you know. Sometimes I find my own mistakes. For branching, the inputs are ALU of 1, ALU of 2, branch, 0 flag, and then the output is PC source. So this is the output, and these are the inputs. So we have 16 possibilities, right? So 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, and finally 1, 1, 1, 1. Okay.
I'm lost too. Don't worry, I'm lost too. I need to figure this out slowly. So okay, then I get it straight. Everything that's not a 0, 1, or 1, 1 will be 0 on that. What is the flag? You need to get that. So that's what it's right.
The what? The 0 flag? If it is, if they are equal. Yeah. Yeah. So 0 flag will be 0. Yes.
Although, can you explain how the A and the feeling of 1 and 2 so 0, 1
Red is 1. 0.
What does that mean? Well, technically, well, if ALU of for some reason is like 0, 1. Well, in that case, yeah, you're right. So branching should always be equal to 1, right?
It's not a 0.
Yeah, branching will always be equal to 1. So this condition, you're right, you're right. So we'll ignore these. Right? Similarly, we'll ignore these. Yeah, so I think you can consider that as don't care.
Okay. Why would we get exactly, yeah. So B Q that's going to be 0. So when it's 0, 1, 0 is 0, right? That means that it's not 0, so it's going to be 0.
Yeah.
And then the next one. So then for alien 1 is 0, alien 2 is 1, branch is 1, 0 is going to same for the last one.
All right. So shall we fill the truth table now? Okay. So when ALU of 1 and ALU of 2, when they are both zeros, then that means it's a load store instruction. Should the branching ever happen in that case? No. So PC source can always be 0 for those. When it is 0, 1, then that means it's a branch of equal instruction. So branch is equal to 1. If the 0 flag is not set, that means the two registers are not equal for the branch of equal instruction. Should branching happen? No. No. So 0. It's a branch of equal instruction and the 0 flag is set. The values are equal. Should the branching happen? Yes. It is an R type instruction. Should branching happen? No, we don't want branching. If it is a B&E instruction and the zero flag is not set, meaning the register values are not equal, should branching happen for branch if not equal? Yes. Correct. It's a branch if not equal instruction, but the zero flag is set. That means the register values are equal. Should branching happen? No, 0. So that's your quick fix truth table. And then from here, you may take a level up and make Cardinal maps and determine your hardware, but this is not the course for it. That was ACP 71. The takeaway message from this slide is how the PC source is generated as a function of ALU of 1, ALU of 2, branch, and the 0 flag. That's the only takeaway message from this slide. So are we doing good? Signed up? Okay. All right. So we can have a separate discussion on the side if some things do not make sense in this slide. But this slide explains how the PC source is generated. Okay. Now, let's proceed further. That's all I wanted to cover lecture-wise. And just a heads up, your next quiz is on November the 1st. The next quiz is on November 1st. And these are the only two things that I explain out of you. Whatever we have done so far, you should be able to explain the single cycle data path for these instructions that are in your project number 4, alpha and beta, add, sub, branch if equal, branch if not equal, add I, load word and store word, meaning you should be able to trace the paths. That's how you're going to explain the data path. You're going to trace the paths, and then you're going to briefly explain it that, hey, RS goes into read register 1, out comes the RS value, RT should go actually to the right register. So these are this is how the data path is going to work. And you should be able to generate the control signals for the above instructions. Now, please note that these are the only instructions we are covering in project number 4. So if you get a head start on project number 4, you're kind of done with your quiz preparation. To prepare for this quiz, please start working on project number 4 and review the slides from lecture 8 onwards. So lecture 8 onwards, please review all of those slides and any Zoom recording. Any questions on the quiz? Yes.
Will you be given the hardware?
Yes, you will be given the hardware. You will be given the hardware. And it is going to be open book and open notes. So most likely in the quiz, you will see a question. Please refer to processor figure number 4 and answer the following crazy questions. Right. Cool. Okay. All right. Now, project number 4. Project number 4 alpha is now active for you. And we are going to code for it. And also project number 3, if you're still struggling with it, we are going to do it right now, right today. I mean, in this class. For the next 3 minutes, what I would like for you to do is partners sitting on the right should explain what is going to be done in project 4 alpha. So please pair up. Partner sitting on the right explains to partner sitting on the left what is being covered in project number 4 alpha, and partner sitting on the left should correct or agree with whatever is being covered in project number 4 alpha. I would like for you to be crystal clear with the specifications. So Gafur will explain it to Cairo, Kelvin explain, Sam explain it to similarly, please explain it to Matthew, Marcos to Ben. Alright, so you kind of you can just eavesdrop. Yeah.
Okay, so yeah, something right now.
Should be out. Separated by yes. And that develops itself. Or the register alpha files. I can understand why this is here because just that's why line and code. Shouldn't these be zeros and ones? Like basically
well, the requirement is that I would like to do the decimal trips.
so this I scan the first.
Are you talking about shouldn't those be binary?
Yeah.
So
Yok Allah, bu the Real site alsam.
Because I don't want to wrestle with so by using the decimal values,
So stand by.
so this depends on the register display setting has been chosen as decimal. But that's a very good question.
Binary ya. Yani sen aktarılmalıysan yine instruction.
All right. So Ben, here, okay. All right. Okay. Now jazz hands just one more time. We're almost there. We're almost there to do our coding. What I would like for you to do is take a piece of paper, and I would like for you to write down the tips to successfully complete project number 4. What, in your opinion, would be the tips, programming tips, to successfully complete project number 4? Share those tips with your peers.
So see the first one is everything is all sound values for VP values, right? So what it is, I kind of associate the picture. The register 0 is
Just a second. So please write the tips. I will randomly ask the groups of students to share their tips.
This array, that is the first element. This is 0 element, right? The first one should be out. So whenever I want the register values, I want to add
because when you do add, sub, add, the register value changes, right? So those are the values.
Yes.
So we are considering first is 0 to 7. And the binary file should be by either alpha.
When I say I want to pick 0, I want to
Okay, and then the one that's from the 3, right?
Yeah. I want to X 0, 1, 2, 3. What I do is as I'm iterating this course, I update it. Yeah. Yes, exactly.
So please write down the tips, the programming tips that you think will help you and your peers. Let's work together. That's not a tip. Let's discuss together. That's a great tip.
birinci operation.
Please take 1 more minute to write down top 3 tips that you think will help you and your peers with coding for project number 4. Use your experience from project number 3.
You're almost there. Yeah, almost there, but yeah, but we'll fix the.
We'll fix today. We'll fix today. All right. Okay, so jazz hands. Jazz hands one more time. Jazz hands, guys. Come on. Okay. All right. Now, let me summarize what's going to happen in Project 4 Alpha. Project 4 Alpha is a preliminary MIPS simulator. It's a preliminary MIPS simulator that inputs a machine code and outputs what should be the value of control signals to control the data path for those inputs, and correspondingly, what will be the register values, because register values are going to change. The instructions we are going to focus on in project number 4 Alpha are add, sub, and the ADA instructions. So quite straightforward. So there's no branching involved, and therefore the program counter will just simply increment by 1. What your program should do is it should read in the machine code, identify, well, I'm getting too fast. Read in the machine code, read each line by line, identify what the machine code is about, meaning what instruction it is trying to perform, what are the target registers, what are the immediate value, if any, and then do the computations according to that instruction. And at the same time, set the control signals for that instruction. Yes. Kind of, yes, very good. So that's a very good hint, actually. In project number 3, you were given a MIPS code and you had to convert it into machine by looking up the dictionaries or by looking up dictionary values using the keys. Here in this case, you have to go the opposite way. You have to use the zeros and ones to identify what kind of instruction it is. So you have to use the values to find out what the keys are, right? So that's actually a very good tip that Mo has indirectly given us. Now, I would like for us to share some tips. So let's see. Amr and Jason, do you have any tip to share? Just one tip is good. Okay, have a chat with each other. Have a chat with each other. It's okay. We'll circle back to you. So, Mo, would you like to share the tip?
So last time I did this one.
Uh-huh. Okay, so would you say that the dictionaries that we have been using in the previous project are still useful? Okay, very good, Marcos. Okay. Okay. So perhaps, how about this? Our dictionary of register values maybe also, right? Because we are using our 8 registers, those are going to change their value. They are all set to 0. So would dictionary be still a good data structure for that? Because registers will store values now. So registers are going to store values, right? So we have to store those values somewhere. So what kind of data structure can you think about?
Oh, because we're gonna explain it.
Yeah.
I would just replace the, like I said, like
Okay.
this, like, make that take the red couple highlights,
Okay. Okay, okay, all right, all right. So let me share some of my tips. So tip number one, keep using the dictionary and dictionaries that you have been using in project number 3. You have used those dictionary for the encoding purpose. This time we have to use it for decoding. Now this is another useful tip that you'll be using, or you can use. Use the read lines function. Now what the read lines function is going to do, it's going to read the entire file and it will store it in the list where each line is an entry in the list. For example, the first line is going to be at location 0 in the list. The second line is going to be at location 1 in the list. Having pre-read the entire assembly machine code, what it will help you do is it will help you find out what is the maximum limit to which your program counter can increment to, right? And as an program counter is kind of like an iterator. So lists are a wonderful data structures through which you can iterate. So please consider using read lines function. Tip number 3, I'm having you perform decimal based computations. So what you can do is use the bit string module to convert binary string to decimal. Tip 3 can be useful for computations because when you're reading machine code, some of the values will be zeros and ones, but they will be in the form of a string. You will have to convert a binary string to a corresponding number. For that, consider using bit string. This is just a tip. You may have your own method, but tip 3 can be a fallback option. To find more about tip 3, please see Canvas supporting materials, Python supporting materials. For computation. Between register values, when you say add RS is equal, when you do add S1, S2, S3, you're adding the values of S1 and S3, right? So you have to perform the computation. Now the values of S1 and S3 are binary. They may be binary. They could be binary. For example, a branch of equal instruction, right? So the immediate, that's actually a binary value. But when you read it from a file, it's going to be a binary string. So you have to convert that binary string to a decimal number so that you can perform easy computations. Right? You could convert the binary string into a binary, but then you'll have to do addition in binary. And that's crazy, right? So it's better to move it into our decimal domain and do computation. Yes?
Yeah, we'll have to have another at least.
So in this assignment, you will only work with register 0 to 6. Very good question. So those are the only registers you'll be worrying about.
So we're not worried about which letters.
No.
It's gonna be $0.
Yes, yes. So Sam has brought an important point here. So with regards to your registers, we are only going to use the 8 registers, and those are numbered registers. We are not going to be using any S or T or what have you. We are going to use $0, which is immutable because it is 0. We are going to use $1, $2, $3, $4, $5, $6, and $7. That's it. These are the only 8 registers that your code should focus on for simplicity. Okay. All right. So these are the 4 tips. I have already uploaded these tips on Canvas. And perhaps the most useful tip that I will give you is please start early and work with the professor, right? Work with me and we can be successful. So let's code for the next half an hour. Time is 11:15. Please let's code and have a discussion and keep making progress with our code for the next half hour.
So the values of all registers start with 0.
Yep. Mm-hmm.
So.
The ones that you want to use within this project,
Right.
and then set them all together, and then we would update the dictionary.
So, well, so some of the dictionaries you'll be just importing from the previous project.
Right.
there was one dictionary that you may have used that gives you the corresponding binary for each register, right? So for example, yeah, T0, and similarly $1, $2, $3, the corresponding binary. So that's a dictionary that you'll just take in. The reason why you would use it is to identify on which register you're going to perform computation on, right?
So we would still keep the corresponding.
You'll still keep that register intact.
But would we change the value instead of what it is to?
No, we are not going to change anything to that. We are not going to do any changes to that. What we are going to do is we are going to create a new dictionary, and we'll call it reg file, right? Where at key 1 resides the value of register 1. Key 2 resides the value of register 2, and so on. And key 7 resides the value of register 7. And initially they're all set to zeros. Now let's say that you want to update the value of register 7 to a new value. Let's
Put the registers corresponding data, like for example, T0 is, let's say 8. We would then update it, all those zeros with the corresponding plot to 7.
No, I think we are still confusing, right? Okay, all right. So let's rewind, right? So these registers have addresses, and those are 5-bit addresses. They never change, right? They never change. But at these addresses, you can store 32-bit values. They can change. So the register dictionary that you'll be importing from your previous assignment, most likely that's a register that gives the corresponding addresses. For example, T0 is address 8, T9 is address 9, or whatever, right? Those will never change, right? Never. What you would be doing now is creating a separate dictionary that will display the value, or that will store the values at these registers. So the previous register you use to reference to these registers, and the other dictionary will be used to store values at those locations, right? So think more, and you need to create another dictionary, but you're not going to change that previous dictionary that should be bringing it in. Okay, yeah,
Thank you.
yeah. Hey, Ben.